All right, so we started the recording, and this is the continuation from last class. We are gonna continue the solution of the forces and moment MCQ paper. So I think after finishing the idea of the moment thing, I asked you to attempt this part first. We discussed some problems from 3.3, if I'm correct. So I'll take problems from 3.3 first, and then I'm gonna go to the top and start going from there. So anyone, do you have any question from page number 17?
No.
Page number 17, anyone? $18.
Sir, 10.
Okay, number 10. A cable car of weight W hangs in equilibrium from its cable at point P. The cable has tensions T1 and T2 as shown, whose diagram correctly represents the forces acting out at point P. So since T1 and T2 are labeled as tension, they will always be going away from the connection point, which means considering as tension, T1 should be going in this direction, upward right, and T2 should pull the rope from the point P to the leftward down. So these are the two directions. So if I just first decide on the directions, then we can easily go forward for the solution part. So let me just label those directions over here. This one is gonna work this way, and this is gonna work this way, and what is gonna work this way. And according to the question, all of these three things produce equilibrium. W is in equilibrium. So we need to have a vector triangle where all these three forces have appropriate alignment, direction, and also they should be placed in a cyclic order or continuous order, so that would represent that closed polygon, or in this case the closed triangle. So all of these in all of the four figures, we have W in downward direction, so W is not a big deal. T1 should be upward right. We have these two options, upward right. So these two are out of the question because T1 direction is wrong over here. Alignment is good, but the direction is shown downward left. T1 is not going to work downward left. And then you have to find out that in which direction the T2 is working. T2 should work downward left, which is available here. And if you look at the triangle thing over here, you should see that this is the only triangle which shows all the three forces in a cyclic order. Have a look. This is the anti-clockwise order over here. And you have a closed triangle. So B is your correct response. বুঝা গেছে?
Yes, sir.
Good. তারপর, anything else from page number 10?
Yes, sir. Number 12. 12, no, sorry, 11.
Sir,
বলো
sir, 10 এ একটা confusion একটু।
বলো বলো কি কনফিউশন?
স্যার যে T2 টা স্যার আপওয়ার্ডের দিকে কাজ করতে পারে না স্যার?
Ideally no, because whenever we define tension of at a certain point, tension on a body always works outwards to keep that body in extended or about to be extended scenario. If you consider for a junction point of connected bodies, from the junction point, tension always works outwards. This is something similar like that. If you try to visualize this scenario exactly for a practical case, let's say there is a this is a cable car. So let's say over here we have another pole. Let's assume that, let's say somewhere over here we have one pole, and let's say over here we have another pole somewhere. So there'll be a taut rope part over here, there'll be another taut rope part over here. So the reason these strings are going to be completely taut is because this string is going to pull on the P point, and this is going to pull onto this P point as well. So I mean, let me elaborate this thing, which might as well, it's actually worth some discussion because it's part of mechanics, so I might as well discuss this. If I take out this figure, let's say if we consider this one, if you try to draw the individual force diagram of multiple components that would be involved in this scenario, let's say if I want, let's say if I show you the additional part of this entire weight system, I can attempt to draw this rope to be like this, let's say in a straight line, and this rope might as well be like this in a straight line in the same direction. So and let's assume that we have two pillars which are supporting this, and let's say this is happening on a hill surface, so you're trying using the cable cart for to move people. I think let's say this is a hill or mountain or whatever. So you have one pole that exists over here, and maybe you have another pole that is existing over here. So one of the key part that you really need to understand, that if you consider it that multiple components only for themselves, for example, this T2 tension is working on the lower wire. So if I want to draw the lower wire exclusively, let's say if I only draw the lower wire, which is this one, this wire this wire, I mean, if you say that there's tension in the wire, this one needs to be shown in this manner. The tension should be working for this body in the outward direction because rope is taut. If the tension was working inward, ধ্রুব তোমার ভয়েস চ্যানেলটা মিউট করো, খচমাচ শব্দ হচ্ছে। Thank you. So if the tension forces worked inward, then we would have this rope become slacked, but it is not actually slack, it is actually taut. So the forces has to pull them outwards so that the rope is taut. So this is the force that exists within that rope. However, if you want to show the force diagram for this segment, let's say here is the junction point P. So for this point, I mean, the pull of the force should be towards this direction. This is the force onto the object when you are considering that this P point is pulling on the object, and this support point of this pole, this is also pulling onto the rope to the left. So the two forces which are experienced by the rope, which is happening from the outside, is these two. Whereas if you consider for point P is experiencing a pulling force from the wire T2, because the wire T2 because of its own elastic property is going to try to come back to its original state. So if you try to pull it outwards, by Newton's third law is going to pull backwards as well. So the rope is under an outward force, which is tension, which is keeping the rope taut, and by Newton's third law, the reaction force is what is working on the point P. Another way, if this doesn't make good analogy, another way that I can tell you is that, let's say I am experiencing weight and I'm sitting on a chair. If I sit on the chair, I'll exert a force on the chair surface, and the chair will give me an equal and opposite reaction in the upward direction. So if I want to represent that, what is the force that is caused by me on the chair, that should be downwards, and what is the force that is caused by the chair on me, that should be upwards. Something exactly like this is happening over here. So if I draw this, all the three different forces for point P, all of these three forces are going to be in upward direction, because you have to understand that for you to have equilibrium of forces, you would require these two forces to cancel out each other. If any of this force was pushing inwards, you wouldn't be able to cancel them out. Or in another logical way, I can tell you that no, that cannot be a scenario for a cable car. No, never mind. Yeah, that's what I wanted to say. So this is also, I'm trying to make you understand, or I want you to be able to distinguish these two scenarios. Does it make sense? For a single rope or for the junction, the difference between them?
Yes.
Yeah.
Sir, single rope part বুঝি না।
The single rope is going to experience force that is exerted on the rope that is coming from external bodies other than the rope itself. The rope cannot exert force on its own self. So the rope is experiencing the force that is coming from the tip of this bar and this P point. Both of them are trying to pull the rope outwards. Hence, these directions are like this, which is keeping the rope taut. In other words, I can say that any object on its own, by its own virtue, cannot experience a force. An object can only experience a force by the interaction with the second body. I mean, you push something, that is what we can call action force, and that object is going to give you an equal and opposite force. That's what you're going to experience. You're not going to experience the force that you create. You can only get the reaction force that you create. You can only get the reaction force of the action force that you create. বুঝা গেছে?
জি স্যার।
আচ্ছা, সাদিয়া বুঝছো?
স্যার এটা বুঝেছি, বাট স্যার একটু কনফিউশন আছে।
বলো।
স্যার ওয়েটের জন্য তো মানে ওয়েট যে নিচে ফোর্স দিচ্ছে, মানে ওটার জন্য T2 তেও পুল করছে না স্যার, মানে পুল হচ্ছে না ওটা। তো অনুভব করে বলতে গেলে T2 ডাউনওয়ার্ড অ্যাক্ট করছে এমন বলা যায় না স্যার।
T2 is pulling that connection point to the left. T2 is not pushing. I mean, if this was a pushing force, then why should we have this angle in the first place?
স্যার পুশ না স্যার, স্যার মানে যে ওয়েটটা যে পুল নিজেকে মানে নিচের দিকে ওয়ার্ক করছে না,
Yes.
তো T2 এর উপর পুল করবে না।
Weight is a singular force that is one of the three forces on the point P. T1 is the tension of the upper wire, T2 is the tension on the lower wire. Weight and T2 are not codependent, or weight and T1 are not codependent. T2 and T1 are not codependent. They are individual forces coming from individual sources or individual point of contact. If you want to divide these forces into components, what you can have, what is going to have only a vertical component downwards, because what is a perfectly downward force. T2 is going to have an upward component, rightward component. T1 is going to have a downward component and leftward component. So if you try to divide this into components, the upward component of T1 should be equal to the downward component of T2 plus W. So I can write that T1 upward should be equals to T2 downward plus weight. That should be your vertical forces situation. So these two parts are not codependent on each other. These parts do not affect each other anyhow. But if you're trying to develop the equilibrium of forces equation, these two components are going to work in the same direction, but they are not controlling each other's value by any means.
বুঝেছি স্যার।
Clear হয়েছে?
Yes, sir.
আচ্ছা, ঠিক আছে।
আচ্ছা স্যার,
Yes.
Isn't the tension existing because of the weight of the object? Because the object is exerting a force on the rope because of his weight.
Yes.
And so otherwise, if there was no weight, then the tension would not exist, like with the object. So isn't the tension kind of dependent on the weight?
Well, the idea is that, I mean, as far the situation is given to us, I mean, there would essentially exist a tension in the rope provided there is some sort of weight. I mean, if you consider that this object doesn't even exist, which is not connected to this rope at all, there is only a rope over here. Now, if you consider that the rope does have weight, then for an ideal case, the rope might as well get a slack condition like this. Let me draw this with green maybe. So the rope might as well look like a slack condition like that. The rope might look like this because of its weight component. It is possible for the rope to have a curve like this. But if you consider the rope is also weightless, then the rope is very much free to move around, like floating in the air or something in space. The only way you can have the rope in a set orientation is because if you do exert the property of mass, which results into weight onto the rope, which is gonna give it a tension property that will be built within itself.
Yeah, but then wouldn't the value of weight affect the value of tension?
Okay, I see what you're asking now. I didn't think of that. The value of weight should affect the value of tension, yes, and also the alignment is also important. Yeah, the value of weight will also work on the value of tension. Yeah, that's correct. But the direction is always going to be outward from the point P. I said this information wrong. I mean, when I was trying to get at this equation, so I should have said that the direction of weight and the direction of T2 are not codependent. The magnitudes are codependent. My bad. I mean, weight is always going to work downwards, and this tension, irrespective of the position of the weight, this tension is going to always work to the left. I mean, for example, if this cable car had an orientation something like this, if I draw this with, let's say, black a certain black line, let's say, if we have a situation like this over here, and then another way over here, and the weight actually shows up over here. If this is the scenario, in that case also the tension is going to work away from the junction point, and this tension is going to work away from the junction point. So this is going to work that way. So the weight will not essentially cause the T2 to become inward. It will always cause the T2 to become outward. That's what I meant.
Okay.
বুঝতে পারছি?
That's it.
আচ্ছা।
Sir, last line টা আরেকবার repeat করুন।
The weight of the object is never going to be causing the T2 force to work to the right or towards the junction point. The tensions are always going to work away from the junction points. Okay, one of your classmates actually asked for number 11, so they're going to go for it. The diagrams represent systems of coplanar forces acting at a point. The lengths of the force vectors represent the magnitudes of the forces. Which system of forces is in equilibrium? So to find out the equilibrium, we just need to be able to find out a scenario where multiple forces produce equilibrium. Now, there are many different ways we can achieve this thing. We can try to create triangle rule and see, polygon rule. We can try to create polygon rule by measuring by measuring the length of the individual forces considering the length of those arrows represent the magnitude of the forces, and try to produce a closed triangle. We can try to do that, but individually trying to, I mean, that's one way to do this, which is very much applicable. But the most easier way to achieve this, the solution of this problem, is to go for a much convenient version. The convenient version is that, which I showed you in the last class, that if you have three forces produce equilibrium, then it is always true that the sum of any of the two forces should be equal and opposite to the third. Try to understand the meaning of this statement. I'll say it again. If three forces produce equilibrium on an object, then the sum or vector sum of any of the two forces should be exactly equal and opposite of the third, so that together they can produce equilibrium. So what I mean is, can be also written as something like this. Let's say if you have three forces, let they are A, B, and C, and if you say that they produce equilibrium, then if you take the sum of any two on the left side, on the right side the other thing shows up as a negative. For example, I can write that in that case B plus C should give you what? Minus A, right? Which means the resultant of any of these two forces should be exactly equal and opposite compared to the other force, so that whenever you are going to add all three of them, you're going to end up with 0. So this is a much easier logic to apply, provided you understand what this means. In how can we apply this logic? Have a look. For this figure, preferably drawing parallelogram with appropriate choice of sides can prove to be pretty easy. What I mean, I'll go option by option. I mean, there can be so many different examples for you to think about, but I'm going to cover these 4 options since we have them over here. Have a look. In this case, we have 3 forces. These 2 forces are perpendicular to each other. We can very well see that, although they do not show us the 90-degree, but they apparently look perpendicular, vertical and horizontal forces, 2 of them. And the other is at a bit of an angle. So what we can do, or in other words, what we should do, is that we can try to complete this this what? this rectangle, in this case, which is going to be a rectangle. Let's say I'm going to control this rectangle, complete this rectangle. So by using the, I'm trying to apply parallelogram rule over here. And in that case, the resultant is going to look like this. This is going to be our resultant. And we can try to find out whether this resultant is exactly equal in length of the opposite arrow, and do they exist on the same alignment. We can check this out. If that logic is fulfilled, then that will be a correct answer, which for this question exists at option choice A. B, C, D will not work out because of multiple reasons. I'm going to show you these things. In B also we have three forces. Two of these forces apparently are in perpendicular to each other, so we can try to complete this this polygon, which is going to be a rectangle over here, and the resultant of these two forces, so I'm applying parallelogram rule using these two sides, the resultant of these two forces is going to work upwards in this direction. So it's going to be vertically upwards, but if you measure the length, so if you just look at these two lengths, this is not exactly equal in magnitude for this one, so B cannot be your answer. For C as well, I mean, to be honest, you could have drawn the parallelogram over here, you could have drawn the parallelogram over here as well, but I chose these two sides because completing a rectangle is apparently less time consuming and easier to draw compared to a parallelogram to exact measurement. So the same thing can be attempted for an option to C as well. You can try and complete this rectangle over here, and you can essentially find out the resultant, which is going to be somewhat like in this orientation, and you can measure that whether that these two lengths make sure these two lengths are equal to each other or not. So this would not be equal either. As for the third scenario, there is no, I mean, there are not, there are, I mean, we do not have 90-degree in between any of the two vectors over here. So all that we can do is try to find out, sorry, try to find out the resultant of any of these two forces, and we can check this out. Now you can choose any of the two forces that we have over here as per your wish. But what you necessarily have to do, you have to draw parallel lines. So you can try to draw a parallel line or a horizontal line over here. Yes. And let's say I'm going to draw another parallel line over here. From here, that is going to be parallel to this side. Drawing parallel lines can be done by sliding a ruler uniformly over the piece of paper, because we're trying to approximately find out these numbers. We're not trying to exactly find out these numbers. So you can draw this parallelogram, or if you have a compass and you are good with compasses, you can go ahead and pretty fast draw two arcs which are going to intersect each other, and you can also find the cross point of the parallelogram. You don't necessarily have to draw these lines if you're using a pencil compass, which also works. Now, what the reason I have drawn these parallel lines, I mean, this one parallel to this one, and this part is parallel to this part. The reason I'm drawing it this way, because I want to find the resultant of these two forces, and I'm going to compare that resultant with the third force and check whether these two things, the resultant of the first two and the third one, they are opposite and equal to each other altogether. So we're going to check that out. So what we can do, we can draw our resultant. Let's say I'm going to draw it by purple. So we can draw a resultant from the origin all the way up to the original point. So you can, let's say I have this much over here. And now if you use your ruler to measure the length of this thing, or if maybe you are going to have a different alignment might be messed up, or length is going to be messed up. So this is the whole idea. All of these three options are not going to be okay, because for these two options, the lengths are going to be definitely messed up for the parts that I have calculated. For this part, the length is also unmatching. This is the only case where you will get the matching value. Now, the problem that the kids in most cases suffer is that because whenever they do not complete these figures, A always appear to be a non-preferable choice. What I mean is this, have a look. If you just look by your eye, it doesn't feel like that the resultant of these two can be equal to this much length. This length of arrows look pretty long, doesn't it?
Yes.
But if you actually complete the parallelogram using the tip of this arrowheads, and eventually if you measure the diagonal length over here, you're gonna find out an exact value over here. To be exact, if any of you have printed the worksheet in 100% without any squashing effect, and if you measured the length of these two sides, you're gonna find them that this is 4 centimeter and this is 3 centimeter, and so the result is supposed to be 5. But it's not essentially it has to be this way, but it happens to be that much if your printer is 100% printout. So that's how we can solve this problem. Questions? এনিওয়ান? বুঝে গেছে তাহলে?
স্যার
হ্যাঁ বলো।
স্যার ফোর্সেস ইকুইলিব্রিয়াম তাহলে বুঝবো কিভাবে? দুইটা ফোর্স একসাথে পরে রেজাল্টেন্টটা ইকুয়াল হলে ওটা হলো কি ফোর্স ইন ইকুইলিব্রিয়াম।
দুইটা ফোর্সের রেজাল্টেন্ট যদি থার্ডটার ইকুয়াল এন্ড অপোজিট হয়, the logic that I build up over here, the sum of any of these two should be exactly equal in length and exactly opposite to the direction of the third one, so that those two things added together can give you 0.
So answer
ওকে স্যার।
কি B?
এটা কারেক্ট আনসার হচ্ছে A.
মনে হয় না।
You can check. Although I don't have a ruler with me, but I can try to show you. I can actually try to show you the length of these two parts to be nearly equal. Let's say if I can do this, can I do this? How do I zoom? Okay, I'm gonna select this segment, and just because we have to, I'm gonna copy this up as well, and I'm gonna paste it somewhere else. Can I not paste it? Okay. So let's say I'm gonna measure. I'm gonna make it horizontal and check whether these two parts are equal to each other, roughly equal to each other or not. Do I have a ruler? I do not have a ruler. Can I use this? I cannot use this. Anyway, so since I cannot use a ruler, so I'm gonna use more geometric thing to prove my point. So what I'm gonna do over here, I'm gonna take this part, take one of this part away, and I'm going to exclusively, let's say I'm gonna take this much out and try to check whether it is equal and opposite to this arrow or not. Take a look. You can now see the left side a little bit. Then if I just cover it over here, the right side should be popping up. So here is the right side corner and here is the left side corner. The diagram is a bit shimmered because I did do it by hand. But if you draw it with your ruler measurement, you're gonna always get the equal length. Anyway, it doesn't appear to be. That's the paradox that you have. It doesn't appear to be a correct answer, but this is indeed the correct answer, because for all the other options, the result of any of the two forces, no matter which two you choose, is never gonna be in the same alignment either, or it might not be. Even if it's in the same alignment, it will always have mismatching lengths. So you're not gonna get any of the two vector sum to be exactly equal and opposite to the third. So you cannot get a zero resonance scenario for B, C, or D. বুঝা গেছে? বলো মান, কোশ্চেন থাকলে বলো, or we can move forward. Anything else from this page number 19?
Sir, could you help in number 12 as well?
Which two vector diagram represents forces in equilibrium? Which two vector diagrams represent forces in equilibrium? Do you know the how to judge from a vector diagram to check whether forces are in equilibrium?
No, sir.
You should. Did you do last class?
Yes, sir.
Did you do the Polygon Rule class?
Sir.
Sorry, yes or no?
Yes, sir.
So the basic idea for Polygon Rule is that if you have multiple forces and if you stack them up one after another, which means you start the new forces from the endpoint of the first forces, and at the end of the placing all the forces with appropriate scale and direction, if you get a closed polygon, you can say those forces produce a zero resultant. So if you want to have multiple forces produce a resultant zero or an equilibrium, you should have a closed polygon, and all the forces should be in the same sequence because you're going to place every forces one after
Sir.
another.
Sir. Got it. Thank you, sir.
Yes,
Thank you, sir. Got it.
বুঝছো?
জি স্যার।
কারেক্ট অ্যান্সার কোনটা হবে তাহলে?
অ্যান্সার সি হবে।
হ্যাঁ, সি হবে, ঠিক আছে। কারণ এখানে কারণ পিতে হচ্ছে in the P option we have these two in one sequence but this one in the reverse, so this cannot be for individual force equilibrium. This can be the resultant force calculated for these two components, but that we're not looking for that. We are considering each of these three are individual forces working on the object, and we are trying to find out whether the object is in equilibrium. So you need the forces to exist in the same sequence. So in R the forces are in an anti-clockwise sequence, in S the forces are in a clockwise sequence. So that's that. Yep. Acha, anything else from this page, anyone? আচ্ছা, এটা তো আমরা আচ্ছা এই দুটো রিপিট কোশ্চেন actually, so it's not a big deal. 15, আচ্ছা এই জিনিসটা নিয়ে তোমাদের সাথে আমার কথা বলা হয়নি। কথা বলা হয়েছে রাফ ওয়াল, রাফ গ্রাউন্ড, এটসেট্রা এটসেট্রা?
No, sir.
No, sir.
আচ্ছা এই জিনিসটা একটা থিওরিটিক্যাল একটা অ্যাসপেক্ট আছে, আমি থিওরিটিক্যাল অ্যাসপেক্ট একটু বুঝাই। This is not a part of the notes, this is a part of the worksheet 11 discussion, that's why it didn't pop in your notes part. So let me just show you what I mean. Whenever we place a ladder onto a wall, I'm gonna take this figure and use it for my purpose. Or actually, never mind. Let's say I'm gonna keep this figure over here. I'm gonna do my own figure and try to make sense with you. So try to understand. Let's say we have a wall and we have a floor. Being wall and floor, these are the two parts. So let's say if I give some hash marks over here representing that this is the solid part, and the right side and the top side, these are the open parts. Sorry, my bad. Okay. So we're gonna try to, and let's assume that onto this wall and floor, we have a ladder that is kept in this orientation. Let's say that ladder is drawn with red. Let's say this is the ladder over here. Now, what we want to judge and find out, will this ladder remain in equilibrium? Or simply put, will this ladder be able to hold its position at this scenario? So to judge for that, we are going to consider each of the surfaces, wall and also the floor, to have friction and not to have friction one at a time. So because we have two different variables for each of the surface, wall or floor, and we have altogether two surfaces, so the total number of cases we're going to see are 4. So what do I mean by this? I mean, we can judge we're going to try and see what is going to happen to the movement or to the forces available on the ladder if the wall is smooth and the floor is rough. So if both of them are smooth, let's say, that's one scenario. Then another scenario can be where both of them are rough. That can be another scenario. Then you can vice versa them. So we are gonna then check for how the forces are gonna work out if wall is rough, floor is smooth, and then we can also check for what's gonna happen if the floor is rough and the wall is smooth. So we're gonna see 4 different scenarios of force calculation. Before I move into the idea, let me just give you some basic concept. The first thing that I need you to understand, assuming that this ladder is a uniform ladder, So let's assume that the weight is working exactly at the midpoint. So I'm going to label that weight with a downward arrow. I have to draw this arrow with. Let's say I'm going to label that arrow with with a brown arrow. So let's say this is the weight of the ladder. Now, what I really want you to understand and appreciate that because of the weight component of the ladder is going to necessarily try to fall down. Now, if the ladder has to fall down, how would this end move and how would this end move? Try to answer that question. How is gonna in which direction would the base try to move, or in which direction is the top end is gonna move? বলুন তোমার বুঝছো আমি কোশ্চেনটা কি বলছি?
স্যার আবার কোশ্চেনটা একটু বলবেন।
হ্যাঁ, কোশ্চেনটা হচ্ছে যে let's say the ladder is placed in this orientation and let's say now the ladder is falling closer to the ground. And if that happens, how would these two ends, the top and the bottom, how would they move?
So how would they?
Move.
The upward part will move downward.
Good. And the bottom?
It will move towards right.
Towards right.
Towards right, exactly. So there's the first information I need you to visualize, that if this ladder starts to get closer to the ground, or if it falls towards the ground, that top end is gonna rub against the wall and it's gonna start to fall downwards, and this bottom end is gonna rub against the floor and it's gonna slowly move to the right. This is gonna happen. Now, why is this important for us to understand? First thing first is that if these two surfaces are both rough surfaces will try to work against friction. They're gonna try to oppose friction. So they're gonna try to oppose motion. So which means if the ladder actually falls down, or if it even tries to fall down, if both of these things are rough, let's assume that both for the time that both of the surfaces are rough, both the wall and the floor is rough. In that case, the frictional force at the bottom at this end should work in this direction, to the left. Why to the left? Because the motion of this base is going to be to the right, so the frictional force of the base is going to work in this direction. Similarly, the frictional force of the wall is going to work in which direction?
Upwards.
It has to work upwards. Can we establish that much?
Yes.
If you disagree at any point, or if you have confusion or question at any point, please respond. No big deal. You don't have to raise hand, you can just pause me. So this is the friction force for the wall. So these are the two possible direction of frictions if friction exists. Now, whenever we're going to consider other variations, for example, let's say if we consider a scenario where the wall is smooth and the floor is rough, we're going to simply consider that this force would not exist. If it's a smooth surface, there would be any friction, and vice versa, So that's one part. There is another part of the equation as well, because
ওই ওয়ালটা স্মুথ হয়, ওয়ালটার ফ্লোরটা যদি রাফ হয় তাহলে ফ্লোরের ফ্রিকশনটা বেড়ে যাবে না?
তাহলে ফ্লোরের ফ্রিকশনটা থাকবে, ওয়ালের ফ্রিকশনটা থাকবে না। I mean, বেড়ে যাওয়ার কোশ্চেনটা আসবে সেই কেসে কখন, যে whether the friction is going to be more or less, that will be coming up from the surface finish and the material of the floor, and also the base of the ladder. So whether the magnitude is going to increase or not is dependent on how hard the ladder pushes the ground. So that for that will require mathematical values, numerical values to find that out, that whether it's in magnitude increases or not. For the discussion that I'm about to make, I'm not going to talk about the magnitude variation. I'm going to prefer to talk about the direction variation, and we're going to try to find out the equilibrium scenario based upon that. Now, why am I going to talk about direction scenario? That question I'm going to answer in a while. So bear with me. So this was the weight. This was the weight W. Okay. So these are the two possible directions for the frictional forces. The other force which will be also involved in this case, so to understand, this part of the ladder is essentially pushing against the ground, because weight is working downwards. So this end is pushing against the ground. This is the horizontal surface. So the force that the ladder exerts on the ground is vertically downwards. And the ground by Newton's third law will also push and vertically upward force onto the ladder as well at this point. So I can essentially try to draw this a reaction force from this point that should be upwards. This is the reaction force on the from the ground from the on the base. So I can write this as, let's say, RB. And in the same manner, this part of the ladder is pushing against the wall to the left. By Newton's third law, this wall is going to push on the ladder to the right. So over here, we should also have another reaction force. Let's say I'm going to label this as a reaction force that was horizontal. Why horizontal? Hold on, horizontal কেন? Why this force is horizontal? I'll tell you why.
আপওয়ার্ড হরাইজন্টাল থেকে মুভ করতে পারে।
Because
due to contact force.
this is a contact force, or this is a normal reaction force. The whole name says it, the normal reaction force. The force is absolutely normal with the surface. So the ladder is pushing on a vertical wall along a horizontal direction. So the wall is vertical. So normal to a vertical wall should be horizontal. That's why the reaction forces are working like this. So these are the altogether 5 different forces that we're gonna have. Now, for any case, for any scenario, these 3 forces are always gonna be here. These 2 forces will always be present. But we can apply conditions, or what we can essentially judge whether these 2 forces are going to be present or not. These are the 2 forces, friction forces, so that we can apply some whether it exists or not kind of logic or alteration. But the reaction forces will by default be there because because weight of the object will be an inherent property. You cannot deny that. Because of the weight, the bottom of the ladder is going to push the ground downwards, and the tip of the ladder is going to push the wall to the left. So we're going to get those reaction forces, which are labeled in this figure, not the action forces, onto the ladder. So all of these, so the next thing that I want to convince you, that all the forces that we have drawn over here are forces experienced by the ladder, not created by the ladder. Do you understand that? The frictional force, or at any of the points, top or bottom, can work on the ladder. The weight is also working on the ladder. And the reaction force, which we have drawn over here, are the reaction force that is available from the hard surfaces on the ladder as well. So these are the 5 forces which are working on a single object, which means logically we can try and calculate out their resultant. You can only calculate the resultant of multiple forces if those multiple forces work on a single object at the same time. I mean, if they are not working at the same time, there is no point of calculating out the resultant. At the same time, what I mean by at the same time, let's say there is an object, and there are there's a big stone, and the stone is being pushed in random directions after 10-minute interval by a strong person. So if you do not have all of these variables working at the same point, you cannot find out the resultant of all the forces that will be exerted, let's say, within a duration of 10 hours or any longer amount of time. We cannot do that. So it's important that all the forces should be experienced by the object only, and all of them should work simultaneously, so that we can find out a resultant of those 2 forces. The forces has to be time-wise intact, accurate, and they have to be existent as well. So these are the 4 different things that can happen. Now, if I try, I might actually try to put this a bit down, because I'm gonna need that segment. So the reason I move this over here is that if I now try to find out the resultant of these 2 forces, I do not know their magnitude, but let's assume that these 2 forces are have non-zero values for the time being. Reaction force have some value, and the frictional force with the wall also have some value. So if I try to resultant of these 2 forces, in this case, these 2 forces are perpendicular, that resultant is definitely gonna exist in the upward right direction. Can we agree on this much at least? I mean, this resultant could be working this way for a very small friction, very large reaction force. This could work this way for a very small reaction force and for a very large friction value. But you can only have that resultant working in the upward right direction, not in any other direction. Can we establish that information? everyone?
Yes.
So I'm talking about directions over here. So let's say I'm going to label this direction as a resultant force over here. So let's say this is one force. And in the same way, at the base, at the bottom of the base, we have the reaction force working the vertically upwards and the frictional force is working to the left. So if we try to assume the possible resultant of these two forces that's going to work on the base of the ladder, that force should definitely work in the upward left direction. So I can try to draw that force by, let's say, which color should I use? Yellow. You cannot see yellow. Did you use green? No, we didn't use green. So yes, I'm gonna go for green. So this resultant force coming from RB or FB, that is gonna work in upward left direction. So we don't easily cannot easily say in which direction it's gonna work, but it is possible it's gonna work in the upward left direction. Now, just because of the sake of the argument, let's say I'm going to place my upward left direction along this one. Why am I gonna do it along this direction? There is a reason for this. The reason is like that. Try to understand. This is a resultant force that exists at the bottom. This is a resultant force that exists at the top. This is the weight. So if you consider three forces which are working on the ladder, two of the forces are working at the side, and the weight force is working exactly at the center. Now, one of the logic that I did tell you in earlier classes that for the for an equilibrium of moment, multiple forces should definitely go to the same point. I mean, multiple forces means if you extend out the line of action of the multiple forces in an appropriate way, then they should all coincide somewhere. So that is why am I quoting this information? Because if this ladder has to be in equilibrium at this state, then the intersection point of these forces, let's say this one, and this one, the intersection point of these three forces should definitely pass through one single point. So what I'm going to try to figure out that is it possible to achieve? I'm not saying this will happen. I'm trying to figure out, is it possible to happen? So yes or no kind of question scenario, not what is happening. What I'm going to try to judge, is it possible to happen, or I mean yes or no. So let's say to complete the diagram, I'm going to extend the weight line along this direction, perfectly vertical or nearest to vertical. Hello? What did I say like just this moment? Did I say random stuff?
No, sir.
I phased out a little. So this is the cross point of the weight line and the reaction and the resultant of the top point. So logic should tell us that for this object to be in equilibrium, for this ladder to be in equilibrium, let me just make the ladder a bit thicker. That might be a bit I mean better understandable. Let's say the ladder is a thick structure. Okay, so these are the force lines that we have. So for these three forces to produce an equilibrium of moment, no, I'm not saying talking about equilibrium of force. For these three forces to produce an equilibrium of moment, all of these forces should pass through the same exit point. Now we have, if the reaction force of the top and the weight of the object, these are coinciding over at this point. So is it possible that this force, which is aimed upward left, to somehow go through this point? I mean, I'm not saying it has to happen. I'm trying to ask you that, is it possible for it to happen?
Sure, হইতেই তো পারে।
হইতেই পারে, তার কারণ হচ্ছে this is aimed at the upward left direction. So if I just extend this out a little bit, and if we have a situation like this, so I'm gonna label this with green, and I'm gonna rub off all the unnecessary parts of this figure. For example, drawingটা করে আসলে ভালো হতো। So never mind, we can still work it. So it is logically possible. I'm not saying this will definitely happen, but it is logically possible that these these arrows uh, আচ্ছা হ্যাঁ ঠিক আছে so it is possible to achieve, which means if both the wall and the floor, both of them are rough, then we can essentially have the object to be stable, which is a basic regular understanding for ladders that we stick sorry ladders that we stick to a wall or a vertical structure, and we can climb up through the ladder, because this is typically possible to achieve. Now we're going to see the other cases, that what if we do not have this privilege of frictional forces. So I'm going to try to copy paste this figure and use different parts of it for my discussion. Let's say I'm going to copy paste this much, and I'm going to rub off the unnecessary parts. Now, so this is the scenario where both the wall and the floor, they are both rough. Okay, let's say in another scenario, the only the wall is smooth, Polygon friction 9, so only reaction force, and let's say the ground is also extremely smooth, so ground going to be reaction 9, ground the reaction করতে হবে. So we can have two different scenarios over here. My question is, if this is supposed to happen, can we make these three forces coincide with each other? Try to have a look. I'm gonna try to extend out this force. I'm gonna try to extend out this one, and the extension of this one cuts the y-axis, cuts the y force right over here, right over here. Now the question that I want to ask you is that, try to think about it. The resultant of the base, which is coming from RB and yes, the resultant of this of the base, the resultant at the base point, provided that the floor is absolutely smooth, will also miss out its frictional component, which means at the bottom point, you will essentially have one single force that should be working vertically upwards. That is going to be exclusively which one? What is the name of this force? Come on. This is the R part of the figure. So এই figure আমাদের কোনো রকম friction নাই, তার মানে হচ্ছে আমরা এটারে actually বাদ দিব. So the frictional force is missing, and here we have the reaction forces are on the W কি জন্য নিয়েছিলাম? B was for base, acha wall. So reaction force for the wall is gonna be there, and reaction force from the and also reaction force from the floor is also gonna be there. But my question is, is it possible for these three forces to have a common cross point? Before you answer, I'd like to remind you, weight is working vertically downwards and this reaction force is working vertically upwards. We already have two parallel forces. So I'm asking the question again, is it possible for these three forces to coincide at a single point?
No, sir.
It is not possible, which means if the floor is rough and also the wall is rough, and if it actually stick a ladder onto the floor and the wall, this ladder is going to start sliding down and it will eventually come flat with the ground. So in this case, you cannot stop the motion. The friction force not being present, they're going to move pretty fast. So that's the scenario. Now, if we go for the other two variations, where we are going to talk about what if we have a rough wall and sorry. So now we're going to see the two other cases where we will consider there is friction present in one and the friction is not present in the other one. So I'm going to copy up this figure one more time. Let's say in this scenario, we want to judge how the forces are going to work out if the wall is smooth but the floor is rough. Get the point? the wall is smooth and the floor is rough. Let's say we try to figure that out. So for that situation, obviously this frictional force would be absent because the wall is considered to be pure. So we are going to only have the RW, or the reaction from the wall force, in our expenditure, and also simultaneously the weight is working vertically downwards. Now have a look. Since I have erased of the force part, so the resultant force coming from the top of the ladder is essentially and exclusively the reaction force. So let me erase all of these parts because we are not gonna need that. So now I have to understand, this force is going to be definitely horizontal, this force is definitely going to be vertical. So we know the exact orientation of these two forces, so I might as well extend it outwards and find out a possible cross point of the reaction force at the wall, from the wall, and the weight. Now, if it is possible that the resultant of the other two forces actually can pass through here, then we can say there would be equilibrium. Hello?
Yes,
Yes, sir.
Sir.
So here, this is the possible cross point of these two forces, reaction force from the wall and the weight. Now the question that I'm trying to ask you is that, is it possible that the combination of the resultant of these two forces, the forces available at the base of this figure, is it possible that this resultant could actually pass through this point? I mean, is it possible to happen? I'm not saying this has to happen, but is it possible to happen?
yes, sir.
You should
See,
be able to
sir.
see that it's possible to happen, which means with appropriate design, it is possible for the ladder to actually stand on the ground and lean against the wall, provided there is significant friction in the কি বলছিলাম? Acha. So in this case, these three forces can actually make equilibrium. So this was the case where the wall was smooth and the what was the other thing?
Floor was rough.
The floor was rough. So that's this scenario. So if you recall, if you give a bit of a recall, for this case equilibrium was possible, for this case equilibrium was not possible, and for this case equilibrium is once again possible. So we have one more situation go by, one more figure to go by. That would be let's say I'm gonna copy this all up. So let's say I'm going to edit this figure in a way that I'm going to consider that the wall has friction, but the floor does not have any friction. So so I mean, বুঝছো কি বলছি আমি?
Yes, sir.
হ্যালো, পোলমান
জি
বাকিরা,
স্যার, বুঝেছি বুঝেছি।
Yes, sir.
ঠিক আছে? So এখানে আমরা যে কাজটা করবো সেটা হচ্ছে we're gonna obliterate this friction, assuming that the wall is rough but the floor is smooth. So if we obliterate this friction part, so let me show you. Let's say this friction simply doesn't exist. We don't have anything over here other than our personally owned land or real estate, however you want to put this, and then we want to get rid of this friction, but this friction should be there. So just because so that I do not make a confusion over here, I'm gonna rub off the green line because it's important. Okay, so if the floor is smooth and the wall is rough, we're gonna have this thing coming out of the floor. And because the floor is absolutely smooth, there's a frictional force. So the only force that you can get at the bottom of the ladder is gonna be the reaction force from the ground. Now I'm asking you, and this over here was represented as as a possible cross point. We didn't fix up the how many fans or how many lights are gonna be in the classrooms, which we can take advices from you. I'm saying weird stuff. My bad. So in this case, what I want to remind you that we have the exact similar problem what we had over here. The main reason why that we could not make a cross point is that these two forces were parallel. Do you remember? weight was working vertically downwards, and the reaction force of the floor is also working vertically downwards. So in this case, it is impossible that these two forces will ever cross. Hypothetically, we say that these two lines can cross at infinite distance, but that's not essentially the scope of our answer, so we're not going to go there. Similar thing is also happening for this case as well, for the last case as well. So for this last case, I should not even have a resultant ঘোরাঘুরি plan. I'll tell you why. Acha. So being parallel forces, they are not going to coincide. As a result, this cannot also this situation is not going to give us equilibrium as well. So if I summarize all of these figures over here, I can tell you a couple of things. So try to listen to me and try to understand the meaning that I'm saying. For a ladder that is leaned against a wall, we will definitely require ground friction for the ladder to be in equilibrium. Anytime if the ground is smooth or frictionless, the ladder simply cannot stand. এই কথাটা কি বোঝা যাচ্ছে? For the case number 2 and 4, have a look. We consider that the floor is absolutely smooth, or there's a frictional force. And for both of these cases, the force available at the bottom point was exclusively the reaction scenario. So ultimately হয় নাই। But এই চারটা ফিগার নিয়ে কার কোনো কোশ্চেন থাকলে বলো। Anyone? No one? আচ্ছা ঠিক আছে। Let's say we don't have any question about this part. So let's say we're gonna try to solve this question right now. Now give the question a try and see if you can sort this out. It would be a nice idea to at least give an arrowhead direction for the possible direction in the possible direction of the resultant force available at the top of the ladder and also available at the bottom of the ladder. The question says what? Rough wall and rough floor, right? Rough ground. So the resultant force that will be available at point P is going to be upward left, and the resultant force that is going to be available at point Q is going to be upward right. And from G point, our weight is going to start working. So they're asking us that which vector triangle represents the forces on that ladder. The first thing first, weight should always be vertically downwards. Weight cannot be anything else. So we can discard one of these option choices using that logic. Which one is that?
Sir,
D.
D.
I didn't ask about the correct answer. I am asking you that.
না স্যার বললাম ডিসকার্ড করা যাবে যেটা সেটা bolu.
Exactly. But one of you actually answered the correct answer, which is also good. So we can discard D because weight should be working vertically downwards. So D bar. And then you can understand that the forces at P point should work upward left and force at Q point should work upward right. In which of these questions do you have those directions perfectly properly shown? And also the
স্যার
force.
একটু লাউডলি বলবেন।
আচ্ছা
স্যার শোনা যাচ্ছে না।
hold up a second, আমি একটু আসতেছি। You please try to think about the question. Sorry. So which one is the correct answer, do you think?
স্যার আমার মনে হয় এ।
এ হওয়ার কথা।
বাকিরা সবাই দেখো
এ
মানে বাকি অপশনগুলো কেন হবে না সেটা কি ফিগার আউট করতে পারতেছো যে কেন বাকিগুলি হবে না?
জি স্যার।
ইয়েস।
সো ল্যাডার সিচুয়েশনটা বুঝা গেছে, ঠিক আছে? So let's go for the next question. Anything else from this page? Did I show you how to attempt this kind of questions? I mean, for minus vector, how do you deal with negative vector?
বুঝলা দিকে যাবো।
স্যার এটা প্রবলেম আছে।
17.
ইয়েস স্যার।
আচ্ছা দেখাচ্ছি, don't worry. I was a bit sleepy, so I brought in mama noodles and I'm cracking a piece out of it. তোমরা কে কে কাঁচা নুডলস খাও?
আমি
এখন আর খাই না।
গুড।
স্যার খেতে যে একবার আম্মুর হাতে আম্মু মেরেছিল, তো তারপর তো আর খাই না।
ওকে, স্যাড স্টোরি।
I agree.
কাঁচা নুডলস খাইতে অনেক মজা, টু বি অনেস্ট। Anyway, so what I'm gonna do, I'm gonna take this out. And I'm going to make it into minus q. How? Like this. Raise it up over here. And I can essentially get rid of this. So I just reverse the direction, and in the paint, I can easily do this by double flipping it. So this will be minus q. Now you can simply find out the result of this figure. So draw the parallelogram and find out the resultant. D is your correct response. বুঝা গেছে?
ইয়েস।
Sadia? Okay, move on. আচ্ছা, এটা তো হাবিজাবি কোশ্চেন, এটা হাবিজাবি কোশ্চেন।
স্যার এরকম এমসিকিউজ এর জন্য কতক্ষণ সময় নেওয়া উচিত আমাদের, যেখানে ড্রয়িং করতে হবে না অল স্টাফ?
2 minutes. I mean, whenever you're coming across this problem for the first time, you are essentially quite slow. I'll tell you why. Because you are doing this type of figures, I mean, this level of figures for the first time. You are just learning how to do that. So one of the important bit is that whenever you see this figure, you have to sort in your head that what I'm gonna do. Am I looking for a complete triangle that where all the forces work in a single order, in the same order, or am I looking for a resultant force figure? What am I actually looking for? And then you have to figure out the logic. Then you have to go for and search for the logic. So there is a thought process that takes time because you're doing it for the first time. But as you will practice over the duration of the 4 mocks and everything, you should become seasoned, and that way you would know the moment you read the question, you would know immediately that what is it that we're gonna do for that question. So in those cases, you will not require that much time. বুঝতে পারছি?
জি স্যার।
So for drawing kind of questions, there is no, I mean, magical thing that can speed up the process. It's all about practice and confidence. Anything else from this 3.3? Rest of the questions are quite similar and self-explanatory. 21 নিয়ে কেউ বিরত করছো? Anyone? 21 এর কোশ্চেনটা খুব বিরক্তিকর। এটা কারেক্ট আনসার দেওয়া হচ্ছে মনে হয় এ, বাট খুব পারফেক্টলি একলো কারেক্ট আনসার এ হয় না। দেখাই। In this question, they're asking us to find out what should be p plus q. And যদি p plus q কে খুব carefully আঁকি, let's say I'm going to select a q over here, bring it up exactly over at this end. Okay. Now if I try to complete the resultant, this gives me a very faint downward line. I mean, because I have a my MS Paint over here, you can see that this downward direction is visible. Do you see that? I mean, this is the downward line. Now we are losing pixels. This is horizontal. This is perfectly horizontal, where you do not have any pixelated thing. Now, if you slightly put it a bit down, then you have a bit of a bit pixelated line. So now you can see it's slightly downward. But in the actual exam hall, being able to draw this figure with this much precision is a nightmare. And they have given really two options which are pretty close to each other. One is both of them has the exact same equal length, A and C, and they are both working to the right, which is also good. But one of them is slightly working downwards, the other one is slightly working upwards. But the correct answer for this one is working downwards. And this is more commonly mistaken by kids just because they rush through the process. Maybe they didn't have enough time in MCQ paper, which is quite common. Don't be alarmed by that. So এটা একটা প্রবলেম হয়। পরিমাণ তোমাদেরকে আরেকটা কথা বলি, আমি মনে হয় আগেও তোমাদেরকে বলছিলাম, সেটা হচ্ছে যে and all of you, both of your paper 1 and paper 2 exams are 1 hour 15 minutes, and in paper 1 you will be answering 40 MCQs in 75 minutes. In paper 2 you will answer a paper worthy of 60 marks in 75 minutes. এটা কেন বলতেছি, if you think in direct unitary method, for every MCQ question you have practically 1 minute 45 seconds, because the total duration of hour you are gonna go for is 75 minutes. 75 minutes it means 1 hour 45 minutes. Nah, sorry, 75 minutes মানে কত? 75 minutes, আচ্ছা 75 45
1 hour 15 minutes, sir.
আচ্ছা ভুল বলছি, 75 divided by 40 করলে কত হয়? দেখো তো, 75 divided by 40 করলে কত হয়?
1.9 minutes.
1.875. Now 1.875 to a fraction. So I'm going to multiply this number with 60 to get it into exact seconds, which is going to be 112 seconds. So you get about, let's say, 110 seconds for each MCQ question. That's the average time that you're going to require. But তোমার সব কোশ্চেনে এই পরিমাণ টাইম লাগবে না। কিছু কিছু কোশ্চেন থাকবে which of the following quantities are vector and scalar quantities. আবার কিছু কিছু কোশ্চেন থাকবে হচ্ছে যেগুলোর কোশ্চেন দেখে মাথা ঘুরায় যাবে। যেমন কিছু কোশ্চেন আছে এরকম এমসিকিউ পেপার কোশ্চেন, some questions are so big that the question itself covers nearly half the page. Then there is a simple diagram which easily makes sense, and maybe each of the answer choices are 2 lines. It's not a mathematical question, it's a logical question, but you have to read the entire question, take all the values in your head or take all the aspect in your head, and you have to start reading the answer choices A, B, C, and D, and be able to figure out which one is wrong, which one is correct. Usually what happens, by the time the kids finish reading the option choice D, they have completely forgotten the aspect of the question. It leaks out from the head. So there will be difficult questions, but you will have to spend more time in the difficult questions and save time on the easier questions. That the usual way that I say that if you are well prepared for your exam, now well prepared is a pretty important word because it has a lot of significance, which means you have studied properly, you have gone for the mocks, you know your shit. If you are well prepared for your exam, then ideally to answer 30 MCQs, you're going to require exactly, let's say, 30 minutes. For the rest 10 MCQs, you're going to have the remaining 45 minutes. Now, you might be able to answer 5 MCQs out of those 10 within 20 minutes. Within 20 minutes. So, I mean, you have a total of 45 minutes for the remaining 10 MCQs. So, in those 10 MCQs, you have to sort out you have to figure out how to do them properly. In every MCQ paper, the way CI is currently designing the questions, there will be at least 2 to 3 problems. At least 2 to 3 problems are going to be there, which are going to be long and detailed and difficult because of that reason. So you really have to, spend some time to be able to solve those questions. So they do not give the same difficulty, I mean uniform difficulty level questions. So they said 30 questions which are pretty simple, and 6 or 7 questions which are a bit hard, and then 3 or 4 questions which are quite hard. বুঝা যাচ্ছে? Now
জি স্যার।
I'm not trying to scare you kids. What I'm trying to tell you is that what kind of question you're gonna see. I mean, if you want, you can essentially try the recent year question papers, but we haven't finished. But we haven't covered all the chapters. But once we'll start taking the mocks, or after we will finish our syllabus, which I hope will be finished by September, sorry, October. So we're gonna have a November and December 2 months in our hand for the whole process. So which is a good thing actually. I mean, I really appreciate that. So within this time, we'll attempt to solve quite a good number of past year question papers altogether, and you'll actually figure out that the MCQs are actually designed that way. So yeah.
Sir, that means the MCQ of AS is a bit harder than O levels, right?
Yeah, definitely. Because you're in A level, so you cannot expect that it's at the same level of difficulty. You are going for a much higher degree, so you have to have a higher difficult. You have to answer difficult questions. Yes. The answer to the question is a solid yes.
Sir,
Yes.
what is the total number of chapters in AS?
Well, the syllabus and your book, they have different number of chapters. I usually teach the entire syllabus divided into 11 segments, which I'm comfortable with.
Okay.
For example, I have combined the projectile and the momentum chapter together, because what I found that these questions are show up as a combined question, and then I have combined the force and the moment questions, paper 2 questions together, because they tend to come together. Balance of force, equilibrium forces, division of forces, and then moment or turning effect. These questions seem to get together. So something like that. Okay, we're gonna go for.
স্যার আপনি বলেছিলেন না ওই যে হার্ড কপি দিবেন স্টাফ, তো ওটা দিবেন আর?
হ্যাঁ, ওটা দিব। আমি এই পাঠাওতে রেজিস্টার করছি। আমি এখন আমার সব স্টুডেন্টদের অ্যাড্রেস পাঠাওতে ঢুকানো শুরু করছি। So once that will be done, then I'll print them out and slowly start to dispersing them out. Yeah, I still have that plan and it is to be executed, but I'm too lazy to finish it on time, honest truth. I'll do it.
ইনশাআল্লাহ।
স্যার ক্লাস শেষ হওয়ার আগে আপনাকে যে ইনবক্সে একটা প্রবলেম পাঠিয়েছিলাম ওটা একটু দেখাই দিন।
আচ্ছা, ঠিক আছে, সমস্যা নেই। We'll do the class up to 9:30 ish. Then we'll stop the recording. Then I'll take your answer question. No big deal. You need to class up wait karo. No, দেখা দিও। আচ্ছা, did you guys try this problem, or do you have any question about this one? Do you guys understand the difference between drag and upthrust?
Drag is the force from the liquid and upthrust is drag is basically resistive force and upthrust হচ্ছে opposite আরেকটা force.
Drag is basically fluid resistance, or let's say air resistance is a type of drag. Drag is applicable for cases whenever an object that is moving, actually moving through a fluid and experiences a reverse force because of its motion. Drag is experienced only during motion, whereas upthrust is the apparent weight loss of the object due to the pressure of the liquid. আমি আপট্রাস্টের কনসেপ্ট তোমাদেরকে আজকে ডিটেইলসে পড়াবো না। I'll share
upthrust মানে weight loss.
Upthrust is the reason for weight loss. Upthrust is not essentially weight loss. Upthrust is the reason for weight loss. I mean, weight loss in this case, I mean apparent weight loss.
So basically, the weight or opposite is right?
Yes, upthrust always works upward. Hence the word upthrust.
স্যার মানে বলতে যাচ্ছেন যে আপথ্রাস্ট ওয়েটকে ক্যান্সেল করার চেষ্টা করে।
Yes. In applicable cases, you can cancel it out. In some cases, it will make the weight reading of an object lower than what is supposed to be. In some cases, the upthrust can actually lift up the object. For example, for a helium balloon, gas balloon, basic gas balloon, not air-filled balloon. If you have gas balloons, I mean, the reason the gas balloons go up is because their upthrust is much bigger than their actual weight. So that's why we say they are lighter than the air, or they are less dense than the air. So the atmosphere pushes it up.
Sir, and vicious drag?
Viscous drag is the
Sorry, viscous drag?
viscous drag or drag is the force due to the motion as the object moves through a fluid. It does collision with the fluid particles. That's how we get viscous drag. আচ্ছা বললাম বলো তোমরা কি এগুলো ট্রাই করছো নাকি আমি একটা করে কোশ্চেন আমার পছন্দ মতো দেখা থাকবো?
স্যার নাম্বার 3 টা একটু দেখাবেন।
নাম্বার 3 তোমাদের আলাপ করে নাই না? ওকে, নাম্বার 3 দেখাবো, জাস্ট আ সেকেন্ড।
The force which we exert. 3m plus the force we exert.
I use this example with class 9 to give them an idea about forces. All right. He was our calculating.
3m plus the force which we are exerting.
Well, one thing you need to understand is that you cannot add dissimilar quantities. You cannot add mass with force. You can add two masses. You can add two forces. You can add two accelerations. You can add two velocities.
Just the force that we add, I guess.
It's just one. Either in the voice channel or in the chat channel. Give me some response. How much force do you think will X exert on Y?
F.
That's one response. If the F force is perfectly horizontal, they might be, they are subject to their weight, but the weight doesn't have to do anything over here because I define the surface to be frictionless. So the weight is not essentially playing any role because I'm applying the external force horizontally. One thing that is Adiba Amira correct, but that's not a value. I would like to have a value. What you wrote is an output of Newton's third law, which is very smart and correct response. I appreciate that. But what would be that value in terms of the F number?
F.
1/4 of F.
Okay. I'll help you to sort this out. I'll help you to sort this out, and then I'm going to make this problem easier for you to work with. Try to understand. These two objects are in contact with each other. How much is the total mass here? Total mass.
4m.
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 Remember this.
4m.
You're going to apply a force onto this object, and this F force is going to accelerate the total of this 4m mass. Because they're in contact, it is essentially obvious the X is going to push object Y, and Newton's third law tells us Y is going to also push X. True, but as they're going to move along this plane under the effect of this force F, they must have the same acceleration. Can we agree on this fact?
Yes.
They're going to move synchronously, side by side. So they cannot have different acceleration. Now, if I assume the acceleration of both the objects is going to be A, I can pretty well write from Newton's third law that F equals to 4m into a. Can we agree on this equation? This is the Newton's third law, Newton's second law.
Yes.
Do you guys know Newton's second law?
Yes, sir.
For those of you who don't know this, Newton's second law is the basic version of Newton's second law is F equals to ma, which actually tells us that the mass of an object, the force exerted on an object is equal to the mass of the object into acceleration of the object. This is the basic formation. I wrote 4m because in this case, for my example, I used 3m and another m, so that's why I wrote the mass to be 4m. So this will be my thing. And now if I calculate the acceleration, subject acceleration out of it, the acceleration of each of the object will be f by 4m. So now have a look. This acceleration is true for x. This is also equally applicable for y. Now if I apply this formula once again, exclusively for the two objects, how much force would the x object require to maintain this acceleration? I can write this as mass of x into acceleration of x. Can I write this equation? This is the same equation as f equals to ma, only I'm writing this equation exclusively for object x. That's why I'm using the subscript x. If I replace these values over here, have a look how much do I get. Mx is how much? 3m. What is the mass of x? 3m. And how much was the acceleration? F by 4m.
F by 4m.
So if you do the math, how much are you left with?
3m by
3/4 of f, right?
3/4f.
Check this out. Is this calculation all right?
Sir, I did not understand this calculation.
Up till which part?
Sir, from fx into mx multiplied by ax, from that part.
This is the equation that I've written for exclusively for the object x, which is the basic equation of f equals to ma. But I try to denote this thing using the subscript x because I only wanted to calculate how much force, listen to this part very carefully, I only want to calculate how much force is required by the object x to maintain an acceleration of a. Thank you. How much force is required by the object x to maintain an acceleration of this much. So that I mean, if I write a equals to this is essentially equal to, this acceleration is basically equal to acceleration of x. It is also equal to acceleration of y. Do you agree to this? Both the objects have the same acceleration.
Yes.
So that's what I replaced over here. Mass of x is 3m from the figure. Acceleration of x is this much. I replace that. M and n crosses out each other, so you get 3 by 4f. That's the calculation. বুঝে গেছে এখন?
Yes, sir.
Achha. So this means that to maintain this acceleration, object x requires 3 by 4f for its own. But how much did we apply on object's x side? How much did we apply? F. Out of this f available, f amount of force, it is using 3/4 of this part for its own acceleration. So how much is left? The basic math.
1/4.
F minus 3/4 of f is 1/4. So logic should tell us that this 1/4 of f force should be exerted on the object y, because you are, let's say you are feeding the f object a value of, let's say, 40 Newton. I'm choosing the value 40 Newton because it's a good fraction. We can very easily divide it into 4. Let's say if f is 40 Newton, object x is going to use 30 Newton out of it because that's the fraction, 3/4. And how much should it have remaining? 10. It is
10
going to
Newton.
exert 10 Newton force onto this object. Now let's give a calculation that can we get this number for fy calculation. Let's say if I do the fy calculation, fy equals to how much? My into ay, right? If I go ahead and replace the values, my is m, ay is f by 4m. I'm just replacing values over here. This is replaced as this one from the figure, mass of the y, and acceleration of y was replaced from this part over here. So how much do you get? M and m crosses out each other. You get 1/4 of it, right?
Yeah.
So you can see it very well that once we have applied the f force onto the object x, whatever that value is, I use the 40 Newton as an example. It doesn't have to be 40 Newton. object X will use 3/4 of the available force for its own acceleration, and it will provide the remaining force onto the object Y, so that object Y could also accelerate its own self. The entire logic of this whole point of this whole question was that both of the objects should have the same acceleration since they are in contact with each other. এই পর্যন্ত ক্যালকুলেশনটা বুঝা গেছে কিনা?
Yes, sir. Yes, sir.
লজিক্যালি কনসিস্টেন্ট, ঠিক আছে? আচ্ছা, এখন আমি একটা ব্রেক নিতেছি, it's 7:06, so we'll resume. বুঝা গেছে?
Yes, sir.
Yes, sir.
Any question? Now, what is happening from in this case that for this, I actually didn't look at the question for quite a while, so I messed up the masses over here. Here, X has a mass of m and Y has a mass of 3m. So if you apply F force on X object, X is going to use 1/4 of it for its own acceleration and transfer 3/4 of it onto Y, because this one has 3 times the mass as this one. So the question says, what is the magnitude of the force exerted by block X on block Y? So that is not supposed to be F/4, that is supposed to be 3F/4. বুঝা গেছে? মানে in my demonstrated example, I considered the X to be the bigger object and Y to be the smaller object, but here it is the other way around. So that's why the correct answer should be D. Okay. I'll talk a little bit about number 4. Question number 4 says a car with front wheel drive accelerates in the direction shown. Which diagram best shows the direction of the total force exerted by the road on the front wheels? Try to understand. We are trying to calculate out the force exerted by the road on the front wheel. Try to understand. This car is going forward, so this wheel is going to rotate clockwise. This is a front wheel drive car. Front wheel drive car means the engine is connected to the front wheels and the rear wheels are just attached to the whole body to pull it forward so that it can have low friction. So this wheel is going to rotate like this and it's going to rub against the ground so that the ground would is going to be pushed backwards. So the wheel is going to push the ground backwards, and by Newton's third law, the ground is going to push the wheel in the forward direction, because the wheel is attached to the car body. The entire thing is going to be pushed towards the forward direction. That's how it's going to work out. Now, important bit of the information is that here the correct answer is not going to be C. Why? Because the question says which diagram best shows the direction of the total force exerted by the road on the front wheels. This word total changes a lot of information. What I need to understand, this part of the discussion that I just told you was because of Newton's third law, what is happening for the action and reaction force between the wheel body and the ground. Additional to this force, the ground is also responsible to uphold the weight of the whole car. What I'm saying is that let's say the car has a weight of something which is equally distributed on all of its 4 wheels. So each of the wheel is also pressing on the ground by a certain amount of weight. Am I correct? So each of the wheel are also pushing for a force onto the ground because of the weight of the car. Because of the idea of reaction forces, because of normal reaction force, the ground is going to exert an equal and opposite force onto the wheel at this point vertically upwards. So only because of weight, the weight is a property that is undeniable at any condition. When the car is stationary, then also weight is going to work vertically downwards. When the car is moving at a really high speed or a medium speed or whatever speed, we are also going to have the same amount of weight. And that weight has to be balanced by the road surface, because if the road surface cannot balance that weight, the car is going to slowly start to sink in, which just doesn't usually happen. So at this point, we're going to have one reaction force vertically working upwards and another reaction force, because of the friction and the Newton's third law, should be working horizontally to the right. Now, if you try to find out the resultant of a vertical force and a horizontal towards right, your only possible direction of your resultant force is going to be upward right. That's why B is the correct answer, not A and definitely not D.
Sir, right কেন হবে?
Because
towards right.
Because the car wheel pushes the ground to the left and the ground pushes the car wheel to the right.
আচ্ছা আচ্ছা স্যার বুঝেছি।
বুঝছো? মানে হচ্ছে আমি যদি
জি
এখানে
স্যার।
দেখাই, due to Newton's third law, because of the idea of friction, there is going to be a force in this direction, and to balance the weight of the car, there is going to be another force from here over here in this direction. The resultant of these two forces is going to be in the upward right direction somewhat. That's why B is the correct response.
স্যার
Okay, here
আনসার
is
কি
the
বি?
answer হচ্ছে B. Correct answer হচ্ছে B.
জি স্যার।
A is the normal reaction force of the wheel on the wheel from the ground, and D is the forward force because of running the engine, or actually driving the car. So the resultant of these two, which gives you the total direction, because the question is asking for the total direction of the whole thing.
স্যার
বলো।
স্যার যদি কারটা একটা হল্টে থাকতো তাহলে কোনটা হইতো?
কার যদি মুভিং না হতো
রেজাল্টেন্ট।
তাহলে কার আনসার হতো A, because if the car was not moving, which means the wheels are not rubbing against the ground, the wheels are basically stationary, but you still have weight, so তখন কার আনসার হতো A.
তখন কি ফ্রিকশনাল ফোর্স একদমই থাকবে না?
Well, there is gonna be frictional force existing between the car wheel and the car wheel and the ground, but you are not essentially using that friction to move in any direction. The entire point of rotating the wheel is that so that the wheel pushes the ground backwards and the ground pushes the wheel forward. That's why we have to rotate the wheel. That's how we move from point A to point two, point one point to another point. So if you ask me, will the friction become zero? That answer is a no. There is going to be static friction, but we are not going to have any horizontal forces whenever the car is horizontal or car is stationary. There would be friction existing between the wheel of the tire of the wheel and between the ground, which we call static friction, but this will not result in any direction of force. I mean, let's say it exists, but it does not add to the force, because it's not because the wheel is not trying to move the earth. When the wheel tries to move the earth or the ground then tries to move the wheel in the opposite direction. That's basically what we do to
Sir, if there was no forward force, then would static friction exist?
yes.
Why, sir?
I mean, here's the
স্যার
idea.
আমার একটা ক্লাস আছে, আমি চলে যাই। লাইক আই ক্যান টেক লিভ?
Yeah, sure you can. The physical property for which the static friction exists. Static friction essentially has a maximum limiting value, maximum limit of its value. So the physical property, surface finish and weight and everything, for which the static friction exists, that thing simply does not become change or vanish because the object is stationary. Static friction has a variable range up to its maximum value, that if you apply a small force, is going to give you back a small force, and if you give a bit bigger force, it's going to give you a bit bigger force as well, as long as you do not reach to the limit of the maximum static friction, which is a fraction of the weight, something কি একটা রেশিও দিয়ে ক্যালকুলেট করা ভুলে গেছি। But as long as we define the two surfaces to be rough, or there is a friction between the two surfaces, even when the object is not moving, there would not exist friction that you can measure. I mean, or you cannot measure forces. But if I ask you that the friction is zero when the object is not moving, I think that's somewhat correct, because we cannot measure that friction force, which can actually say that, okay, that friction is zero. But I'm really inclined to say that, I mean, defining friction zero would mean that this is a smooth surface, but that's not entirely true. There is no friction because the car wheel is not trying to move the earth. That's why the earth is not trying to move the car wheel. It's a vice versa thing, because the car wheel is remaining stationary and the ground is also stationary. So they're only working in the vertical direction to balance out the weight. The moment we start to roll the car wheel, that's when the forward force starts to get developed. Do I make sense?
Yes,
Ji, sir.
but when the car is stationary and there's no forward force or there's no force in the car, why would the friction exist, like physically?
What what?
Why would the friction exist when the car is not moving and there are no forces? Like the car could remain stationary even if there is a forward force, as long as the forward force is less than the maximum static friction. But
Yes.
assume there's no forward force at all. So why would the friction exist? Even if it's a rough surface.
I mean, okay. Let me give you an analogy to make sense out of it.
The Earth is always spinning, for which
No. Let me give you a small bit of analogy. I'm not sure if the analogy is going to make sense, but this is the best that pops in, that's popping in my head right now. We need air to breathe. Now, we don't essentially sense air is around us as long as we are breathing. We only sense that we need air to breathe if we are pushed into water and made to stay there for a long enough time. That's when we sense the requirement of air. Now, because we are breathing in air and not sensing air around us, because we can breathe pretty easily, it does not mean that air is absent. But the requirement of air is sensed when there is shortage of air. So you're gonna get a measurable value of a forward force or a forward force, or you can actually measure the friction force whenever you are actually applying a force, and the friction phenomenon, friction, is gonna give you a response for it. But it doesn't mean that whenever you stop applying that force, that physical property is vanished. Frictional force will become zero. If you don't apply any physical force, the frictional force will be also zero. But that does not mean that now between the two objects contact surface has become smooth. Because if I say that the friction has vanished or friction is no longer there, that would mean that if we don't apply the force, the two contact surfaces have become smooth. The moment we're going to start applying force, the two contact surfaces are going to become rough. But that's not the case. Would it make sense anyhow? Did the example make any sense?
Sir, could you hear me out? I have an analogy too.
বুঝি
আমার একটা analogy আছে why there was always some friction.
Yeah. বলো.
So, sir, as we know that the Earth is always moving, there's always some sort of force acting on a body, so it's never constant and sitting there, and thus a friction exists.
I understand in terms of vocabulary what we just meant, but I'm not completely sure about what your idea. I'll have to think about it. আচ্ছা বলো শোনো তোমাদের আজকে 9:36 বাজে, সো আই এম গোনা কল ইট এ ডে। সো তোমাদের নেক্সট ক্লাস কবে? বুধবার না?
Yes sir.
বুধবার দুপুরে।
Yes sir.
তোমরা এই P1টা পুরোটা শেষ করবা এবং P2 থেকে P2তে P2 ওয়ার্কশপ কয় পেজ? 22 পৃষ্ঠা না?
Yes sir.
সো এক্স্যাক্টলি লাস্টের হাফ গুলো করবা। লাস্টের হাফ মানে কতগুলো করবা আমি তোমাকে স্পেসিফিকলি বলে দিয়েছি, নাহলে আবার তোমরা ওলপার করবা। আমি বলে দিচ্ছি, আমি হোমওয়ার্ক অর্ধেক করে দিচ্ছি যাতে করে অ্যাট লিস্ট তোমরা পুরোটুকু করো। আমি র্যান্ডমলি বলে দিতে পারি যে পুরো ওয়ার্কশপ করে ফেলবা, বাট দ্যাট মাইট বি আ বিট, what can I say, a bit
difficult.
No, I wouldn't say difficult, that might be a bit less encouraging. So the worksheet is 22 pages, so if you start from page number 11, you're gonna start from question number 11. Okay, start from question number 11 and finish up to the last. So I'm giving you the last half of the paper 2 worksheet as homework up to Wednesday, minimum this much. If you finish up everything, you finish up the whole one, good. So first you solve the paper 1, complete this to your best capability, then you go for paper 2, and if you are going for paper 2, start from 11 and go forward. Kids, thank you very much for your attention. We will call it a day. You are excused, everyone can leave. And Zara Razwat, you have a question? Oh, hold up. Farhan, what you wrote is absolutely correct. So that's why I read your explanation a little bit earlier, but I was not responding. Yes, Farhan OIS তুমি যেটা লিখছো, this is absolutely correct. So I'll